Thank you, Chris, for this cheering introduction. I hope you're all sufficiently caffeinated for a theory tutorial. And yeah, we'll be talking about first principles theory of transport. I'd like to thank the organizers for having me here to give this tutorial. And let's just start with the talk. All right, so on the first slide, I would like to outline the challenge of, that theorists have if they want to calculate properties of materials in general and materials for molecular electronics in particular. So we start with well-defined models that you can find in textbooks, and to describe particular phenomena in materials, for example, charge transport, this will be the topic of my talk. So this is the Landauer model taken from this textbook. But then we go to reality, and reality is often much more complicated than just these simple and beautiful models. As we heard yesterday, you can have systems like biomolecules that are very complicated. You have huge complexity in the material, and you have an enormous amount of different degrees of freedom. And the question is how to bridge these two worlds, the worlds of the well-defined models and then the other one of real-life systems, which are very complicated. Now, if we would have a theory for transport and we think about what should that theory include and what should it be able to describe, we can make a wish list. We can start with a wish list for the physical model for electronic transport, and we would probably like it to account for many different effects, the effect of bias, temperature. We've heard yesterday in biomolecules about the structural dynamics in these molecules, how the atoms move at finer temperature, which can be complicated and difficult to describe and has many interesting consequences. There are, of course, different regimes of charge transport, tunneling or hopping. There's also diffusive transport. And then there are other types of very interesting physical effects coming from spin and correlation properties of the electrons. Now, my theory should also be material specific because in the end, not only as a theorist, not only would I like to describe what's happening in experiments, in the end, my goal should be to come up with new systems. And so for this, I have to be able to work on these theories from a material specific perspective. So that should include the geometry effects in the system. I've mentioned them. There are also some interesting electrostatic effects happening in these junctions. One example are interface dipoles between molecules and metals. We'll be talking about these later on in the talk. And then there are electronic structure effects, how the molecules couple to the electrodes, how the energy levels in the molecule align to the Fermi level of the metal surface. All of these material-specific parameters should be accounted for as well in my physical theory. Now, one way to do that, and this will be the main focus of the talk, is to work with first principles theory. I will explain what it means, to use it to predict material-specific parameters that then enter physical models to describe electronic transport in these systems. Now, what are first principles techniques? In one sentence, it means that I would like to calculate material properties just by knowing the chemical elements in the system and the number of the electrons. So if you give me a system, this is all I know. I can use that information to, in first principles theories, to calculate any properties, be it electrical, optical, chemical, mechanical, optical, or other ones. Now, in principle, we've been talking about nanoscale systems, so we are interested in how the atoms interact with one another, what the electrons do in terms of transport once they go through these molecules. So I have to invoke quantum mechanics and can write down the Hamiltonian that contains a kinetic part for the electrons, then the interactions with the nuclei, and then the Coulomb interaction among the electrons. And it looks fairly simple, just three terms. But then once you go to practical calculations, this becomes very, very complicated because you have to apply this Hamiltonian to a wave function psi that depends on the coordinates of all the electrons present in the system. So if you have 10 electrons, you have a 30-dimensional object. But then, of course, we have many, many electrons in these molecules and metals. So this object becomes extremely complicated, not only to optimize it in calculations, but even to think about it because it's so highly dimensional. Now, this brings me to a nice quote that I like to show here, and that is, in theory, there is no difference between practice and theory, but in practice there is. So, as a theorist, we like to do things which we understand in principle, but we have also sometimes to do something practical. And this is where the fun starts. And the question is how to bridge these two worlds, coming from quantum mechanics, which is very complicated to use in practical calculations, to actual material systems and predict their properties. Now, one way of doing that is a famous theory called density functional theory, or DFT. And it's just one way of going beyond the challenge of first principles calculations. But the basic idea of DFT is to go away from the many electron wave function to the electron density, n of r, and use it as a fundamental quantity to optimize the system and its properties. Now, note that the electron density is a very simple object compared to the wave function we had, because no matter how many electrons you have, it always depends on free coordinates x, y, and z. So it's very easy to understand compared to what we had on the previous slide. Now, one way to use DFT in practice is in Cohen-Sham equations, and I've written down a Cohen-Sham equation here. And the difference to the previous quantum mechanical Hamiltonian is that in the Cohen-Sham equation and in DFT, it's many often the case that instead of focusing on the many electron wave function, we here have single electron wave function. So each electron in my molecule or metal is addressed by this Hamiltonian individually. Now, how do the electrons interact? Well, I have a common potential, this V effective here. And an important ingredient of that potential is the so-called exchange correlation potential, which is a functional derivative of the exchange correlation energy. This is also where the theory gets its name from, because these energy functionals are functionals of the density. The density I get from these single particle orbitals after the DFT calculation, and this gives me a scheme to calculate material properties. Now, the issue is that the exchange correlation functional, it's unknown, so we don't really know how to write it down exactly. But there are many approximate functionals, and this list I'll show you now just should give you a bit of the jargon that is used in DFT and also in the next slides of my talk. So the first and most famous one is called the local density approximation. Here you have the formula for the exchange correlation energy, and it depends, or it's critically depending on the density at n of r. So that's why it's called local density, because it only depends on the density at the local point. Now, to use it in practice, it has been parameterized for the homogeneous electron gas, which means that for homogeneous systems like simple metals, it's actually working very good. Now, if I have a system that is more inhomogeneous, and we're talking about molecule-metal interfaces, they are fairly heterogeneous, people realize that you have to go beyond the local approximation. They came up with what is known as the generalized gradient approximation. It's called gradient approximation because now not do I include information on the density at point r, but also on its gradient. And this gives me a better description of how the density changes in space and has been shown to improve calculations if you want to, for example, optimize the geometry of simple molecules. So the most common version is called PBE after Perdue, Berg, and Enserhoff. And we'll be also seeing some of the PBE calculations on the slides to come. Now, one issue with PBE, there are several issues, but one issue is that it has not been very great in predicting the electronic properties of molecules and other systems. And that's why developing new functionals has also been very important in this field. And one way to do that is to use hybrid functionals, which means they're called hybrid because they mix these GGA functionals like PBE and Fock exchange from Hartree-Fock theory. And we'll be talking about hybrid functionals also in a little while. All right, so now I have a theoretical scheme how to write down the equations. How do I do DFT calculations in practice? And to show you how, I present this workflow of actual calculations. So a single point DFT calculation, this is what we do when we not optimize the geometry. We just take a geometry and we calculate the properties of the system. How do we do that? Well, first of all, I have to provide a set of coordinates. These are the positions of the atoms in my system. And gives me the geometry. Once I know that, I choose a certain DFT functional, and I've mentioned LDA and PBE, and B-free-lib, probably some of you have heard of it. It's one of the most commonly used hybrid functionals. Then I solve these Kohn-Sham equations using a DFT code of my choice. Again, I apply this Kohn-Sham Hamiltonian to my wave functions. And here I have the critical ingredients, the exchange correlation functional that I've specified here. And in the end, what I get are results of the calculation. If the calculation converged, I will get the total energy of my system, the ground state energy. I'll also get the charge density of it. I can calculate the effective potential of my electrons from here. And then I get so-called Kohn-Sham orbitals and energies. These are the single particle states that appear in the Kohn-Sham equation. Of course, the question is, how useful are these results that you get here for actual transport calculations for molecular junctions? And this will be the main focus of the talk today. So here's my outline. I'll be talking about three aspects of these systems, about their geometries and how accurate they are once we use DFT to calculate them. Then I'll focus on electrostatic effects in molecular junctions, mostly in self-assembled monolayer junctions. And finally, I will talk about how we can predict electronic structure and level alignment in these systems and what are the pitfalls of using DFT for these calculations. All right, so let's start with geometries. Now, let's just go back to one slide, back to my Kohn-Sham equations. I told you that we'll get results of total energy and charge density, but what we often invoke when we calculate properties of these systems is the so-called Born-Oppenheimer approximation. That comes from the fact that in any molecule or a metal, I'll have protons and electrons, and the protons are far heavier than the electrons, which means that their motion in time and space is just much, much slower than the ones of the electrons, which allows me to approximate their interactions to be independent of one another. So I have separate equations for the electrons and the ions. And what this implies is that the ionic positions in my geometry, they enter as parameters into the Kohn-Sham Hamiltonian I have up here. Now, once I assume that using the Born-Oppenheimer approximation, I can use what is known as the Hellman-Feynman theorem. It comes from elementary quantum mechanics. It's an exact theorem that tells me when I would like to calculate the derivative of the total energy with respect to a parameter, I can use this equation, which is fairly simple to implement and to calculate. And since my ionic positions enter as parameter, the derivatives of the energy with respect to the positions give me the forces on each ion in my system. So in any DFT code, this is done basically by default, right after every calculation where you have the total energy, because it's very, very efficient to calculate. And so once I do that, I get the forces of all the atoms in my system. Now, I can use that after each DFT single point run to optimize the geometry. I adapt the positions of the atoms and then calculate the forces. I check the forces. If they are not sufficiently small, I will move the ions by a certain to a new position, calculate the forces again, and then I will do that until my geometry is optimized and the forces are small enough. Question is, this is a nice scheme, but how accurate is this for molecular metal systems and also biomolecules using density functional theory? Now, one important aspect, and I'm sure many of you know this, one important aspect in the interactions of the atoms in these systems are van der Waals interactions. And I'm showing two examples of recent papers that talked about van der Waals interactions in the context of molecular electronics. So one is from the Columbia University group. It's on single molecule transport. And they found that for these pyridine-based molecules, it's important to address van der Waals interactions once you would like to predict the most probable or relevant geometries in the transport experiments they've done. And another very nice example actually comes from Chris' group. He works, as you know, on self-assembled monolayers. And these self-assembled monolayers, often they are bound to surfaces by covalent bonds. But in between the molecules, I mean, how are these molecules standing up? So these molecules are kept together by van der Waals interactions often. And he reported that these van der Waals interactions are important when you would like to address the coupling of the tail group, which is functionalized here to the top electrode. So these van der Waals interactions, they affect the coupling, if you like, between molecules and metal surfaces in single molecule junctions, but they can also affect intermolecular interactions in self-assembled monolayers and many other systems. Now, why is this important? It's important because van der Waals interactions are infamously challenging for density functional theory. We sometimes like to call these interactions, with being theorists, dispersive interactions, and there are other types of dispersive interactions. And to see why it's challenging, let's think about what van der Waals interactions are. So I have an electron density, and since it's a quantum system, I can spontaneously have fluctuations in the density, and these spontaneous fluctuations could be represented by a dipole. Now that dipole could induce at another point in space in my system an opposite dipole, and then the two attract each other. That's van der Waals interactions. Now, why is it complicated for DFT? I was telling you about local approximations and semi-local approximations, which only have information of what's happening here. So I don't know at all what is happening here, and I can definitely not predict how these two will interact because it's inherently a non-local effect requiring information on 2 points, at least 2 points in space. Now, systems for which this has been shown very nicely in the DFT literature are noble gas atoms. As we all know, they can only interact predominantly by these van der Waals interactions. If you look at the binding energy of one of these systems, just 2 atoms, binding energy is a function of distance. What you would expect is the binding energy to go down when it reaches a minimum. This is the distance the 2 atoms will have, and then it tails off to the dissociation energy. Now, if you take a standard DFT, a PBE functional, you find that compared to accurate calculations, most likely these are wave function-based calculations, the DFT theory does not predict the van der Waals interactions in the systems well, and so it definitely cannot account for all of the effects that are happening in these simple noble gas diatomic systems. Now, this is very important for molecule-metal interfaces. I've introduced this for molecular electronics 2 slides ago, but there are other systems, beautiful examples of molecules that form well-ordered monolayers and surfaces. So this is a PTCDA that has been studied for a long time. And this work by Romana et al., they focused on PTCDA on the free noble metals. Now, if you calculate the absorption energy with GGA DFT as a function of the distance of the molecule to the surface, again, you would expect it to go down and predict a negative absorption energy and then go to the dissociation energy. You see at the top the experimental distances that have been measured with X-ray standing wave techniques. But then the theory for all 3 cases, it never reaches a minimum. It basically tells you that the molecule or the monolayer would just be not absorbing at all. Now, this is frustrating because many people have studied PTCDA on noble metal surfaces, and so the theory does not predict it to be actually existing, which is really troubling. Now, this is also important if we would like to take that geometry that we find in the theory and calculate other properties. I'll be focusing on 2 properties, the work function modification. This is, just in one sentence, the work function modification means that as I absorb a molecule, I change the electrostatic potential right above the surface to the pristine surface. And this is important if I'm interested to, for example, inject electrons into the combined system. I have to care about the potential right at the surface. Now you see that if we calculate the work function change as a function of the distance to the molecule, and I take all of these distances that the theory basically said they are almost the same in terms of its energy, you get very different work function modifications. And then if you look at the homo-LUMO energy, how they align to the Fermi level of the metal surface, also these numbers change a lot if I change the distance between the molecule and the surface. Now the reason is that GGA DFT, for example the PBE functional, it does not account for molecule-metal interactions in terms of van der Waals, and since they're lacking and they're attractive, they're missing in the theory, and so the theory cannot account for predicting the correct geometry. Now, this has been known for a while, and so in the past maybe 10 years or so, the theory community in DFT has put great efforts in coming up with new correction schemes of how to account for van der Waals interactions in these systems. And it's not only important for molecules and metals, of course, it's important for many other systems. In this somewhat busy graph, I show you the mean absolute error with respect to a very accurate calculation of various different methods from density functional theory. And I would just like to group those in two classes. The one that are not corrected, which we've seen on the previous slide, and you see the errors are really large for these test systems. But then once you account for van der Waals interactions and hydrogen bonding in dispersion correction schemes, these calculations can become actually very, very accurate. And that's, as I've mentioned, it's not only important for molecules and metals, it's tremendously important in biosystems, in molecular crystals, or in layered crystals, which actually are fairly complicated from this perspective to calculate. Systems like graphene or very thin semiconductors coupled together by weak van der Waals interactions.
Sorry, what's your reference energy? You say correctly, what's your zero?
This is coupled cluster calculations. So this is highly accurate wave function-based methods, which include correlation effects and often serve as a benchmark for these type of calculations from DFT. All right. So what are these dispersion schemes doing, and how can we use them for molecule-metal interfaces? Well, the simplest version, and it turns out to be actually one of the most practically useful versions, are pairwise dispersive corrections. It means that I take my total energy from a DFT calculation and I just add a term accounting for the van der Waals interaction, and that term is computed as a sum of pairwise interactions between each atoms in my systems I and J. So I calculate for each pair of atoms their van der Waals interactions, keeping them together, and then I sum them up to have one total term, E van der Waals. Add it to my total energy, and as you know, since I take the derivative of the total energy with the coordinates to optimize geometry, my forces will change, and the geometry, I find it will also change. Now, you see I have here these parameters. C, R is just the distance between the atoms, but I have these parameters and some other parameters in this expression. And you can calculate these parameters from very accurate methods in the gas phase, but intuitively it makes sense that if you go from a carbon atom in the gas phase to, let's say, graphene, these parameters should change because the graphene is very different. The carbon atom in graphene is a very different one than the one in the gas phase. Now, if I go to graphene to a nanotube, they may also change, and if I go from graphene to graphite, they also change. So ideally, I would like to have van der Waals coefficient that somehow sense the chemical environment the atoms are embedded in. And that was the major breakthrough in our field of Tkachenko and Scheffler in 2009, who came up with a scheme of how to make these coefficients depend on the density of my system. And as you know, I'm calculating the density at each step when I get the total energy. If I know how to adapt those parameters with the density, I can then change or adapt these parameters and calculate the van der Waals energy. And this has been first shown for various different systems in the gas phase to work very nicely. But then another breakthrough came in 2012 when they realized that if you go to molecule-metal interfaces, you have to do something else. That is, the molecule on a metal does not sense the same van der Waals interactions as two atoms in the gas phase because the metal surface has so many electrons that the electrons in the surface screen the van der Waals interaction. So it's actually becoming weaker between a molecule and the surface, as for example, between two molecules in the gas phase. This has been known since the 1960s and 70s. There's a theory called Lifshitz-Zaremba-Kohn theory, and this is what Tkachenko, Scheffler, and others have used to further adapt the coefficients in this formula to include the screening of the surface. One of the first systems they have looked at is again PTCDA on silver, and it's a beautiful system for us theorists because it's so well characterized. And you see here, again, the absorption energy is a function of distance. This is the experimental distance. This was an estimate for the experimental binding energy. You see the quote-unquote old theory that gave this depressing result. But then the corrected theory, it's the light blue curve over here. It shows a nice dip and has a minimum very close to the experimentally found distance, and is also in reasonable agreement with this estimate for the binding energy. So it was a very promising step in the right direction because it really showed excellent agreement for this case of PTCDA on silver. Now, does it work for other systems too? This is one example of what we did in this direction. So right around the time of this method, there was a paper that reported experimentally the distances and geometries of a free layer system. Now you have a silver surface you have again the famous PTCDA layer on top, but on top of that you have a copper Bc molecule, another layer of molecules, different molecule copper Bc. So we get a multi-layered structure, which is challenging for the theory because now the system is becoming even more heterogeneous. So this is how it looks like. You have here the PTCDA molecule on top of the silver surface, and then you have less densely packed copper Bc molecules on top. And to our great satisfaction, we found that the agreement of the theory with the experiment is very, very good using these van der Waals corrections. And this has been shown for many other systems of molecule and metal interfaces. And I'll just mention some of the names of the people who have worked on this. And well, this has been a great success for DFT, for the DFT community. All right, to summarize the first part of my talk, I really emphasized the importance of dispersive interactions, especially for these systems. Once we use suitable corrections, we get excellent predictions of junction geometries. So that's very, very good. Now, this has been shown to be reliable for well-defined systems. I was talking mainly about large flat-lying molecules on metal surfaces. We know from experiments by LEAD or STM how these molecules lie on the surfaces. We have very detailed information. But often we actually use that information to, as I said in the beginning, we have to provide a geometry before we optimize it to then calculate it from theory. And since maybe we can have also discussions for the rest of the week, I also would like to address two open questions from my perspective for more complicated systems. So we've heard yesterday in some of the talks about the complex structural dynamics in these systems. And then the question is, you know, from what I've shown you, I always define one geometry and optimize it, giving it infinite time to relax, and then I calculate its properties. The question is, does this make sense, and is it even possible to define the geometry that is useful and present in experiments or applications of these systems? And the second one, which is related to the first one, is that since we have sometimes very flexible molecules, can we assume that it's useful to take only a single or even a few geometries, and does it make sense to assume that they are in the ground state? Because if I have systems that are very flexible, it makes sense that multiple configurations are very close in energy, and also electronic configurations are very close in energy. And then the question is whether approximations that I have been emphasizing, like the Born-Oppenheimer approximation, is really applicable to these systems. And many people are working on this, and I think it's also a very nice and fascinating area of research. All right. Now, coming from the geometries, now I would like to talk about electrostatic effects in molecular junctions. Now, let's start with elementary physical properties of dipoles. This is something I've been working on as a PhD student and then later as a postdoc. And it's very interesting that, as Amina Tan and Leo Koenig did in 2007, if you calculate basically the field lines of an electric dipole, single dipole, just not applying any DFT, just using electrostatic theory. Here is the dipole, and you see that the field lines, they decay pretty far into space. Now, if you take the same dipole and you make a 2D sheet of these dipoles, you pack them closely together, it turns out that the field lines become much confined. They're much, much closer to the dipole layer than they were to the individual dipole. So an isolated dipole and an ensemble of dipoles, they are very, very different from each other. And that's not something which is really new. It just comes out from electrostatics. This is how it works. And the reason is that if you look at it in more detail, you find that the slowest decaying term in the electric field of such a layer depends critically on the distance between the dipoles. So if that distance becomes small, the slowest decaying term also becomes small. So if my dipoles are closely together, let's say they're 10 angstroms apart from one another, it's 10 angstroms divided by 2 pi, so 1.5 of a distance to the dipole layer that the field is decaying into space. So it's much confined to the dipole layer. And we have to think about self-assembled monolayers. They are often closely packed together, just apart by a few angstrom. So I have to account for this property of dipoles and dipole layer. Now, we can look at this with more beautiful pictures. A friend of mine, Georg Heimel, in a review paper, he has shown this similar idea comparing the single dipole you see it creates a perturbation to the electrostatic potential energy, but far enough away from that perturbation, you have one common vacuum level around the dipole. Nothing special. If we go to a dipole layer, since the field is decaying very, very quickly, we see that at each side of these dipole layers, we have one common vacuum level. And it's the two vacuum levels, they are different. I have now two vacuum levels on the left side and on the right side of the dipole layer. And I have a step in the potential energy, which is denoted here as delta E, which separates the electrostatic potential energy before or on the left side of my 2D layer and on the right side. So these polar layers of dipoles and also polar molecular layers, they generate a confined step in the potential energy. Now, how can I study this with density functional theory? I go back to my Kohn-Sham equations, I solve them, and what I get is the effective potential of my electronic system. What we often do when we look at molecules on surfaces and also surfaces in general is that we make a plane average of the electrostatic energy because, you know, in the direction of the surface, it could be interesting to look at it for other purposes, but if we are interested in how molecules interact with the surface, the most intuitive and useful direction is actually the one perpendicular to the surface. So we plane average in the x, y direction if c is the coordinate perpendicular to the surface, and then we calculate this plane average electrostatic energy, and you see it here for a surface. And so why is this important for the surface? First of all, because as we've also heard yesterday, the surface has a geometrical edge like this table. This is where the atoms end. But then the electrons in my system, they are not bound to be just stopping their motion where the edge of the surface is where the atoms lie. They can tail out into space, and so they create a thin dipole layer at the surface. This is called the surface dipole. And that is something that you can actually see here. Here's maybe the last coordinate of my atoms, but then the potential actually tails into vacuum. And this is this dipole layer of the surface that I was talking about. Now, if we calculate this for metals using density functional theory, we actually find that it's in the work function which quantifies the Fermi level and this dipole layer at the surface. How much energy do I need to get one electron into vacuum? It's actually found to be in very good agreement with experiments, and this provides hope that this will be similar for molecule-metal interfaces. Now, what are important effects beyond the effect that I was explaining with the surface and the density tailing into space? What are important effects discussed in the literature happening between molecules and metal surfaces that could change that dipole layer? Now, one effect is called Pauli pushback. Then we talked about, I've introduced already this idea of polar molecules and dipoles. Of course, they can also change the work function. And then there's bonding beyond these effects and also beyond van der Waals interactions, and that is what I would call chemisorption, that a new chemical bond is formed or charge is transferred between molecule and metal, and that also can change the work function. Now, what are these different effects? Well, the Pauli pushback effect is actually, I went back to 1950, maybe it has been known for longer, but this is the oldest paper I found by Mignolet, who said that van der Waals films of non-polar gases may exhibit considerable surface potentials, and the compression of the electric double layer I was referring to at the surface is been happening when you put these noble atoms on the surface. And so this is what is called Pauli pushback. It means that you have electrons in your molecule or atoms that you put on the surface, and these electrons, they push back the metal electrons into the metal. Remember, these metal electrons are tailing out into space. So they are pushed back, and we call it Pauli pushback because the pushback is mainly due to the Pauli repulsion, that two electrons cannot be at the same spatial position, and so the electrons are pushed back into the metal, and this will change the dipole layer at the surface, right at the interface between molecules and metals, changing the electrostatics in a crucial way. Now, polar effect in molecules, this is, I think, very, very important for biomolecules, and this is one example from the Weizmann Institute, a group of Ron Nahman. They have studied these oligoalanine molecules and chains of them, and you can see that they can have huge dipole moments on the order of minus 40 or plus 20 dBi. So very large dipole moments. And they actually come from individual small local dipoles that are distributed along the chains of these longer molecules. Now, going back to the single molecule versus molecular layer picture I've shown you before, if you have monolayers of these highly polar molecules, you can expect a change in electrostatic potential energy. Now, one example from the group of my PhD advisor, Egbert Zoyer, this is a biphenyl molecule that has a polar tail group at the end. And this is what we've seen before. You get one common vacuum level right around the molecule. But if you take the same molecule and you comprise it into a molecular layer, two-dimensional molecular layer, you find two vacuum levels on the left side, on the right side, and they are differ by the delta E VAC that I've shown here. So the adsorption of polar molecules, it changes the work function because of this effect. While single dipoles only cause local variations, these layers of dipoles can actually result in very large variations of the surface potential. Now, one interesting effect in this context is, of course, depolarization of the molecules that I have when I go into a molecular layer. So I have the field lines of a dipole for single molecules. But if I put these molecules closer together, the field lines start to penetrate each of the molecules. And it turns out that similar to the effect of the dipole being confined to the tail of the molecule, also depolarization is then confined to the tail of the molecule. What it implies is that if I calculate the dipole moment of a single molecule, because of this depolarization effect, the dipole molecule in each molecule of a layer of the same molecule will be smaller because my molecule has been depolarized. But still, it's very large, or results in a very large step in the potential energy once I consider this 2D layer. All right, so molecule-metal bonding, what are the options for molecule-metal bonding beyond pushback and beyond dipole effects? Well, you can have formation of a direct bond. I've been mentioning molecular monolayers. For example, you can have a thiol bond between these biphenyl thiols and gold. You replace the SH with an SAU bond, and this will create changes in the charge density and will result also in a step in the potential energy, because each molecule does it. Each results in a dipole moment, and then you get this step right in the potential energy. Now, you could also have a different effect, charge transfer between molecules and metals. Again, I'm going back to PTCDA. Now, if you go from PTCDA on gold to silver and copper, you change the work function of the metal. The Fermi level goes up, so it becomes more likely that the LUMO of the molecule would be below the Fermi energy, so you need a charge transfer to keep the system in equilibrium. And this is what is happening in PTCDA. So theorists have resolved the charge transfer. You see that it goes into the PTCDA molecule, and that when you plane average or plane integrate it, you see that a substantial amount of charge is transferred from silver to PTCDA. Now, again, this happens at each molecules. They are less densely packed, but still you have a dipole at each side, and that will change the potential energy, change the work function, and other properties of the system. And then a third way of how you can have coupling between molecule and metals is if it really involves a direct coupling between molecular orbitals from the gas phase, if you will. So atomic orbitals from the metal surface, and this has been shown in the case especially of single molecular electronics, where benzene molecules couple directly to leads. All right, so we have these three effects: the Pauli pushback, which is always happening, then the impact of polar molecules, which happens if you have dipole moments, and then monolayers, which are very nicely aligned and build a 2D array of molecules on surfaces. And then what I called beyond van der Waals and pushback, namely chemisorption, once you have building of a new bond or charge transfer to a molecule. The question is, how well are these described when we do density functional theory calculations? And for that, I would like to use the work function as a measure for how well DFT is doing, because the work function, it's quantifying this electrostatic effects I was talking about, because it critically depends on the charge transfer to the molecule. And so we will use experimental data from the work function modification as a measure for how well DFT describes these bonding effects and the resulting electrostatics of the interface. So one example of a molecule that almost purely physisorbs on metal surfaces is copper Bc on gold. Now, gold is very noble, has a high work function, so copper PC mainly interacts via this van der Waals interaction. And we can look at the calculations and the experiment to see that the work function is predicted, even if we just use PBE, it's predicted very nicely or reproduced very nicely by the calculation if we compare it to experiment. Now, again, this is very important to have the accurate geometry. Here we have used these van der Waals dispersion corrections to get the correct distance of copper PC with respect to gold, which you do not get if you don't account for van der Waals interactions, and then the work function may be different. Now, how is it doing for more complex interactions, especially when we have chemical bonding being involved between the molecule and the metal surface? I will show you a few examples, starting with short chains of molecules on, again, on gold surfaces, where it was found that the agreement of the work function modification is again very good even if these interfaces are more strongly coupled to each other. Now, another interesting case is going away from metallic surfaces to other inorganic surfaces, in this case of silicon. We also have chains of molecules on silicon 100, and again, you can compute the work function modification and find it's in very good agreement with what has been found for these systems experimentally. Now, with molecular monolayers, the story is a bit longer, but there was very encouraging work from 2010, and they put a lot of effort into finding the correct geometry of these anthracene selenolate monolayers on gold. There were several geometries that were possible from the calculations, but then they used the calculations to reproduce scanning tunneling microscopy images that were also recorded experimentally to find which of the geometries is the most useful one. And when they used that geometry, they found the delta phi, the work function modification, to be really in good agreement with experiment. So whatever is happening with pushback effects and dipoles due to covalent or ionic bonding in these systems seems to be reliably described once we account for the geometry. But then it turns out it can be more complicated, and one system that we have been looking on recently are open shell molecules. I've talked about them briefly, copper PC and cobalt PC. Now, open shell means that they don't have all of their spin up and spin down states being paired, so you have at least one open shell. And for copper PC on gold, where no charge transfer happens, this can be complicated, but it's not as complicated. It becomes really complicated once you go to systems like metallic surfaces like silver or copper, where a charge is transferred to the molecule. Now I have an open shell system, and in principle, multiple electronic configurations are possible because now I have an extra electron, if you like, in my copper PC molecule, and the question is, where is that electron going, and which configuration is the most likely one? Okay, so you see results. This is the density of states projected onto the molecule of copper PC on silver, singlet, triplet, and doublet, where 3 different molecular configurations we can find in the theory for these copper PC monolayers on silver. And it's interesting that if you look at their properties, they're very different, and at the same time, they're very, very similar. So the spin density of these configurations, we can compute it with DFT, and it's very different depending on each solution. In the singlet, I have up and down electrons being the same, so I don't have a spin density at all. It's by definition, it's 0, so I don't have any interesting spin properties. But then I can compute the spin density of the triplet and the doublet to find that it looks very different, and you can calculate other things like spin polarization at the Fermi energy, and it will also change for all of these 3 cases. Now, the important thing is, if we use PBE, remember these are the GGA functionals, the almost most simple ones we can use in DFT, we only find the singlet, case to be the most stable one. And experiments have been performed on these systems on related surfaces that actually have pointed to more interesting and complicated spin configurations because, for example, a Kondo effect was reported from STM work from ETH Zurich. And so the singlet configuration is not the most likely one, at least that's what we think. And so, but PBE only finds it to be most stable. Now, if we use a hybrid functional, remember these are the ones that mix GGA with Fogg from Hartree-Fock theory. So the exchange interaction, if you like, is described more accurately, and some spin phenomena are also described more accurately. With HSE, we find the duplet and the triplet to be very close in energy, but they have very different spin properties comparing themselves and comparing to the simlet. Now, it's interesting when we look at the table. We see that the work function we find for singlet, doublet, and triplet in PBE and in HSE, they are very much the same. So in this case, I have a system where my spin properties are very different, but the charge transfer itself seems to be very similar, so that the work function modification in the end is also very similar. This also tells me that I cannot only look at the work function as a proxy of telling me how accurate is my theory. There are properties which are more intricate and effects that are more complicated, where I need to look more closely at, for example, spin configurations of these systems. All right, now one other caveat from comparing experiment and theory for molecular monolayers, going back to SAMs on surfaces, has been emphasized in this work that said that Dft calculations seem to consistently overrate the work function changes induced by the monolayers with polar strong molecules. And that's also something that we have found by looking at 3 different molecules. This is work we've done a while ago with Mikhail Charnikov, who is in the audience. We've compared these 3 molecules that have no dipole in the molecule, or a dipole pointing down or a dipole pointing up by orientation of the pyridine molecule. Now, we call them down and up, and they have very similar molecular properties. For example, if you calculate HOMO-LUMO levels, ionization energies, etc., they are very similar. But it's important we have these difference in the dipole moment, because once I make a monolayer, out of each of these molecules, I have different orientations of this embedded dipole. And this is what we can calculate from the calculations. Here you see the energy landscape, this plane average electrostatic potential of the molecule layers on the surface. And we see that they are very similar when we look at the region here. But then after the dipole, looking here, you see there was a step in the potential energy. We can calculate using DFT the core levels that you can measure in XPS, and also find that the core levels of the carbon atoms in the lower part of the molecule are very similar, and then in the upper part they have shifted, comparing the 3 cases of having no dipole or dipole pointing up or down. And Michael and his group have actually measured that in an X-ray experiment, and they find that you see the carbon atoms showing these, the core levels of the carbon atoms actually showing these shifts. Well, this is very nice, because it allows us to sort of probe the electrostatic potential energy along the chain with these beautiful experiments. But when we look at the numbers, we find that in experiments, it's on the order of 1.1 eV, and then in the calculations, it's on the order of 1.4. So the trend seems to be correct. The agreement is not that bad, but still, it seems that the calculation overestimates these effects of molecular dipoles in self-assembled monolayers. And this is also found in the work function when we, Michael and his students have actually measured the work function in 2 ways, found that they are very similar for these systems. But then if we look at the calculations, we see that the trend is very nicely in agreement with the experiment, but then the magnitude of the effect is somewhat larger in the calculation. And most likely that is because we assume really a perfectly oriented layer. There are other possibilities, maybe the polarizability changing. I've been talking about the depolarization effect. Maybe it's not that accurate in the calculations we use. In any case, often we find that electrostatic effects are overestimated. Now, in more recent work with Chris and again Michael, we asked ourselves, well, can we really reveal more directly the consequences of these polar effects for transport? So we studied self-assembled monolayers of biphenyls, now changing only the group at the very end of the molecule close to the top contact, being hydrogen or one of the halogen atoms. This is the X substitution over here. And with that, we tune the molecular polarizability. And our goal was really to uncover the connection between the tunneling rates, potential profiles I've been showing you on the previous slides, and dielectric properties of these molecules using various techniques from transport measurements, surface science methods, and then our job was to do the DFT calculations. Now, these are the results from Chris's group. The tunneling of or currents of these molecules, function of applied voltage. And for the monolayers, we find that the halogen series, they are very, very similar. They show very similar transport behavior, but then the hydrogen system is really larger by almost a factor of 10, which surprised us initially because hydrogen, of all these molecules, if you go back to the gas phase, you compute HOMO-LUMO energies, you find that the gap between HOMO and LUMO is largest. You would expect that this is the worst conductor, but then if you look at the monolayer, it's actually the best. Now, to understand this better and also reveal a connection to dielectric properties, we calculated with density functional theory the epsilon for all of these monolayers and find that it's in reasonable agreement with the experiment. So note that there are some caveats, and if you like to know more about this, I'm not sure if you have a poster today still, Bernie, but just find Bernie and talk to him. He has been working on this for a long time. And what it tells us for us, since the dielectric properties were very similar, we thought there must be a different effect that is responsible for the increased conductance of the hydrogen system. Now, to look at this in more detail, we also computed work function changes for each monolayer with density functional theory, comparing it to photoemission data from photoemission experiments. And the agreement is actually, again, very good in qualitative terms, but you see that the scales are not the same. So the quantitative agreement is not as great. Now, again, the collective effect of the dipoles is confined to the tail of the molecule. I've emphasized this dependence of dipoles on the fields of the dipoles on space when they are densely packed. We see that nicely in plane average potential energies for the different monolayers, and you see that the change really happens if you compare the systems. It really happens at the end of the molecule. It results in a different vacuum energy, and then you get different work functions. Now, if we just look at the molecular layer on the surface and compute the level alignment, so how the HOMO and LUMO line up to the Fermi energy, we find these systems to be very similar. So level alignment does not change with the halogen termination. But then when we add the second electrode in the calculations to each of the monolayers, what we find is that the dipoles they need to be compensated. And what I do is, if I go down this series, I change the dipole in the end and have different potential energy shifts. So that compensation to reach equilibrium between the left and the right electrode was found to be strongest if we have hydrogen. It causes charge rearrangements inside the layer, and that slightly changes the energies of the molecular states in that monolayer. And then we found that this actually shifts the HOMO of hydrogen closer to the Fermi level, explaining its increased conductance. Now, this is interesting because it really shows this interplay of various collective effects. We have the dipoles, we have the pushback effect, but then we have also charge rearrangement for compensations of these dipoles, and all of them together would impact the level alignment, and with that, the charge transport. All right, so to summarize this, when to trust density functional theory for computing electrostatic effects that shape the energy landscape in molecule metal interfaces? Well, we have to account for important effects such as those. Each of them can change potential energy landscapes on the order of 1 electron volt, and how they play together is something that's interesting to reveal and understand if you'd like to control properties of molecules in monolayers. Now, once the geometry is well described, DFT seems to be very reliable, although it could be that the assumptions we use for calculating the geometries are too strong and then prevent us to really have quantitative accuracy for these ensemble of molecules on metal surfaces. And I think it's interesting with all this progress to ask ourselves, how do we precisely quantify energy landscapes? Maybe we've seen the XPS approach by Michael, but maybe there are other approaches by which we can quantify these effects in molecular junction even more precisely. All right, so with the last few minutes, I will address electronic structure and level alignment. It's a very important topic in DFT. And again, we solve the Kohn-Sham equations. We get Kohn-Sham orbitals and energies as a result of these calculations. Now, they are often used in models for transport, non-equilibrium Green's function techniques. The states are used as scattering regions and surface transmission channels once I assume electrons going from the left to the right electrode. And in this way, they determine the transmission and then the current for the junction. And so these DFT orbitals and energies, they are key. They're at least used as key transport parameters in many of the approaches that are used today. Question is, how useful and predictive are these quantities for molecular transport? Now, at first sight, it seems that not very much, because the molecular conductance calculated from DFT is often far too high, as has been shown for this series of molecules. So here you see the DFT result, and the blue curve is the experiment. Only if you correct the DFT result by some scheme I don't have time to talk about, you will find closer agreement. Now, the conductance is really way too high, and this seems to be discouraging. Now, why is that? Well, let's talk about level alignment. What is level alignment? I've been emphasizing these PTCDA on gold or silver surfaces. We can look at it from the top or from the side. Looking at it from the side, we can draw an energy level diagram. We have the states in the metal surface, and then we have the molecular resonances that appear at the surface. And those are separated by an energy from the Fermi level. Now, that energy determines the tunnel barrier and molecular junctions, as you all know. Calculating that is complicated if you'd like to be accurate, because you would have to use something like GW, which is not only very costly and perhaps impossible for systems at the moment, systems like these. It's also very complex and complicated from a more conceptual perspective. Can we get level alignment from DFT? And from the previous slide, you would probably say no, because we saw that the conductances are far too high. Why is that? Well, the group of Jeff Neaton, involving his collaborators Hybertson and Louis, they looked at level alignment of a simple system, benzene on graphite, and they found that LDA calculations using density functional theory, they are far off from more accurate calculations using GW, and the error is really 1 electron volt or so. Why is that? Well, this has been analyzed in follow-up work that compared two different DFT functionals, a standard GGA functional, the PBE that I've already mentioned, then a standard hybrid functional, the HSE functional, and the reference theory in this case was the GW, which is known to be more accurate for these types of calculations. Now we can start by comparing these three calculations for the gas phase molecule, just benzene, and we find that we have the well-known fundamental gap problem of DFT, that the HOMO is too high in energy and the LUMO is too low. If I take these too high and too low energies, I put the molecule on the surface, of course the alignment will be off. But there is a second effect that is causing troubles, and that is now another effect of screening with respect to the surface. If I put now my benzene on graphite, I introduce a Fermi level, I get my molecular energies in GW to change with respect to the gas phase value by almost 1.5 electron volts. So the HOMO goes up and the LUMO goes down. Now, this is not happening in PBE or HSE. They're virtually identical to what their gas phase energies were. And so whatever this effect is, it's not happening in these calculations, so they completely miss it. So this is the impact of substrate-induced screening that is happening. In other words, if I take my benzene molecule, I put it on graphite, again, I have many electrons in my graphite sheet, and they can screen the interactions among the electrons in my benzene molecule. And that shifts the HOMO up in energy. It becomes easier to take one electron out from the system, and it shifts the LUMO down. And again, the molecule has to, or the electrons in the molecule, they have to know that the molecules in the metal change their interactions. So again, this is a non-local effect, and it's not present in theories that are based on local correlation, such as PBE or HSE. There's another problem once we go from benzene, which is in the end a very simple molecule, to more complex systems. I'm again referring to biomolecules, because they can have large dipole moments, and that also involves differently localized orbitals. You can have orbitals which are localized and at one end of the molecules or delocalized over the backbone. And that can also be seen nicely here, where you have orbitals of very different degrees of delocalization in one and the same molecule. In this case, these are amino acids. And why is this challenging for theory? Well, these strongly localized orbitals, it turns out that if you use LDA or GGA DFT, localized orbitals are pushed too high in energy. not only are the absolute energies incorrect, also the orbital ordering can become incorrect, as has been shown some time ago for PTCDA, because there is something called the orbital self-interaction error, and that, if my orbital is very much localized, it interacts more strongly with itself, it destabilizes the energy, pushes it up too far above sometimes the delocalized states, and the orbital ordering can become incorrect. Now, a partial remedy for that are hybrid functionals, where orbital self-interaction error is mitigated, but one drawback of that is that the calculations become much more costly if you go to periodic systems or molecule-metal interfaces. Now, as I've mentioned, this is very important when we have differently localized states. Here you see this is another PC molecule. It's zinc PC on gold. You have the d orbitals coming from the zinc molecule, but then you also have more delocalized orbitals coming from the backbone. And if you use PBE, you see that there is a state appearing here in the calculation which is not appearing in the experiment, and that is partially remedied by using a hybrid functional which can predict more accurate orbital ordering for these kinds of systems. Now, the level alignment is still not quantitative. Sometimes you find errors of HOMO levels on the order of 1 electron volt, as I've shown you with respect to the experiment. So it's really been a long challenge for theory to come up with new and improved schemes of how to predict level alignment at interfaces, as has been emphasized, for example, in this review article. And so many improvements were achieved in recent years of combining different schemes by which we can correct DFT for the errors I've emphasized, the gas phase and the screening errors. Now, in the weak coupling regime, if I only have physisorption, that is has been very successful, because then I can do non-self-consistent calculation. I can do a correction and don't have to update the charge density just to shift the orbitals according to a correction, making them more accurate. But a major challenge was to come up with an efficient scheme that can do the same for Physi and chemisorbed systems. Remember, in chemisorbed systems, we have charge transfer, so I need to update my charge density to compute other properties like work functions. Now, I will just very briefly tell you about our efforts in this direction. We work on so-called optimally tuned range-separated hybrid functionals. These are hybrid functionals which split the interactions between electrons into short and long range via this expression. We get an exchange correlation energy, and you see you have different types of interactions for long-range interactions and short-range ones. And what we do to actually get the parameters in the functional is what gives the approach its name, tuning. We enforce the ionization potential theorem, system per system, calculating the HOMO energy of, for example, benzene in the gas phase, and then calculating its ionization potential energy also from DFT by taking the difference between the neutral and the cationic system. With this, we get the IP, and from the neutral calculation, we get the HOMO energy. Now, we change the gamma parameter here until these two sides of the equation are the same, and then we fix gamma. So we have tuned gamma, but not fitted it to experiment. We have just used one way to tune a parameter, part of the functional. Once we do that, for example, for benzene, we find that the HOMO energy versus experimental ionization potential energy became much, much better. It went from being off by 3 electron volts to being very close to the experiment or GW calculations. And this has been developed in the past year, especially by my postdoctoral supervisor, Leo Kronig at the Weizmann Institute, to show that you can also do similar schemes for HOMO-LUMO gaps, to find excellent results for molecules. But our goal was really to do similar approaches and come up with schemes for hybrid interfaces, molecules and metals, which are very heterogeneous and in which we also have to account for the screening effect. Now, I don't have time to tell you about how we did it, but just in one sentence, I'll tell you that we used this scheme for the gas phase to tune, for example, the HOMO energy of benzene, but then we combined that with an image charge model to account for the screening in the surface. We included that into the calculation of the complete system to get a self-consistent version that we can also apply to chemisorbed systems, and these are the results. First, we started with physisorped systems because they're much easier to calculate and well known from other types of theory approaches. You see the experiments in green, and then you see the traditional theory in light gray. and our result for this case, benzene on aluminum in red. And we find that the agreement is actually very good with our calculation compared to the experiment, has improved a lot compared to the traditional one. Now, since we do this self-consistently, we get a charge density in the end. We can compute a change in the work function, and we find it to be very close, which is very nice because not only did we improve on level alignment, but we also found nice agreement for other properties that are important. So physicist systems are predicted well, and to our great satisfaction, also chemisorbed systems are predicted well. In NTCDA on silver, this is one of the cases where you have charge transfer. You see a resonance at the Fermi energy, which is also captured by the PBE calculation, but then at lower energy, the PBE is really off from the experiment, and our approach has improved this a lot. We couldn't find experimental data for this system, but we have checked it for others, and it seems to be consistent that the calculations also perform well for work function changes, and this means they're not only applicable to chemisorption, but to physisorption, but also to chemisorbed systems. All right, this brings me to my summary of the last part: when to trust or mistrust level alignment calculations, and the short answer from DFT is really never, at least quantitatively, because we have seen that the HOMO-LUMO gap in traditional approximations is too small, and we don't account for the renormalization or substrate-induced screening in these calculations. If you have chemically similar systems, you just change the length of the same molecule. Well, trends can be still very good, but it's important that once you go to more diverse systems, you may have to use novel correction schemes that are really urgently required and have been actively developed over the past years. One remark about orbital localization: this is also critical because it can mess up the orbital order you get from a calculation. We've seen that hybrid functionals, they can partially overcome this issue. And lastly, I would like to also mention that I think the most interesting molecules are those that, of course, have many heteroatoms. We yesterday saw some molecules with copper in it. Now, these often introduce different localizations of various orbitals, and that becomes especially challenging for the theory. All right, so I would like to maybe highlight the main message of my talk. Going back to the framework that we use in DFT to compute properties, I told you that we start with a single point DFT calculation where we perform no geometry. But how do we get the geometry? We get it from experiment, and then we provide a set of coordinates to actually do the whole machinery of what I was talking about the last hour or so. And that's really critical because often we don't know the geometries. And I've been asking these questions in the first part. I mean, how is it even possible for very challenging and dynamic systems to define geometries? Maybe there are also some new experimental advances in order for us theorists to know better how to start these calculations and what effects to take into account in our models. I think that's one of the most important links between experiment and theory in this area. And with this, I'd like to acknowledge my co-workers, my group at TOM, and the two people, Elisabeth and Bernhard, who have contributed to this line of research, and my collaborators from the National University of Singapore, Chris's lab, University of Heidelberg, Michael, and then from the Weizmann Institute of Science, where I did my postdoc, where some of this work was done with Leo Kronig and in collaboration with Jeff Neaton's group from UC Berkeley. Thank you all very much.